Greetings, you are on Power Standard 5, which is the second standard in this unit. It is on orbit and gravity and inertia. And so this is your first introduction to some of those words. And hopefully by the end of the video, all those concepts will completely make sense. There is not a note guide, so go ahead and put on the top of your notebook paper the title, this in yellowish orange there. It says orbit, gravity, and inertia, and put today's date. Okay, so gravity itself. You've probably heard of gravity before, hopefully. So gravity is a force that attracts everything together, not just to Earth, but together themselves. So this is discovered by Isaac Newton a few hundred years ago with the old traditional story of like the apple falling on his head. He's like, why is this apple falling down? Why isn't the apple like going off to the side? Why isn't the apple going up in the air? Why does it always fall down? Well, the apple and the earth were attracted to each other. And so that apple is trying to reunite with its true love. Oh. Okay, so when we're on the planet Earth, which is most of my life, I'm on Earth. Occasionally I do like venture off into other places I can't disclose right now because it's confidential. But when you're on Earth, everything attracts to the center of the planet. So no matter where you are on the world, you always fall down. So if you're on the top of the world, like in the North Pole, you're going to fall down. If you're a penguin and you drop your little egg like they did on Madagascar, then the egg falls down to Earth. No matter where you are in this globe, you fall down towards the center of the planet. So, but again, no matter where you are, things fall down to the ground all around the world. Something we have in common with everybody in every nationality. So make sure you have these notes down. If you need to pause the video, go ahead. Alright, so we don't even just have this thing called gravity. We have a law. In science, if you are a law, you are darn tootin' correct 99% of the time. So we have a few laws in the world for science. Like some other, if you're not a law, you're a theory. So evolution is still in the theory realm of the world because it hasn't been definitively proven. A law, ain't nobody going to disprove this. So the law of universal gravitation, it says all objects in the universe have a gravitational attraction to each other. You're an object. You are. So you have a gravitational attraction to the Earth, which is why if I decide to push you off this building, you're going to fall down to the Earth because you have an attraction to the Earth. You also have a gravitational attraction to an apple. Now, if I drop an apple, the apple's not going to zoom towards you because the attraction between the apple and the Earth is greater. So the apple then is going to fall down. We can test this out. I got an apple for my lunch. It was actually for my lunch 2 days ago, but I keep on forgetting to eat it. It's in my pumpkin. There it is. Okay, so you are somewhere right now. I have no idea where you are. Here's my apple. Let's drop it. Oop! Fell down. Yep, didn't come towards you, did it? The attraction between the apple and the Earth is pretty great. So this apple is trying to get down to the center of the Earth. The ground is probably going to stop it. What else are you attracted to? Oh, a dingo! Dingo ain't my baby. The dingo in Australia. There's a few dingoes out there. They're kind of a wild dog. But you are attracted to a dingo. Do you go flying out towards a dingo? No, I don't think so. We don't go to the down under. You're attracted to King Tut. But you don't go flying off to Egypt or wherever King Tut's body is at. Is it in a museum? I don't know. But you don't. Because your attraction to the Earth. And if there's aliens out there, technically this says the universal law of gravitation. So if there's aliens out there in some far fetch of our universe, you are technically attracted to it. So everything that's anything you're attracted to. You're attracted to a piece of dust. You're attracted to Justin Bieber. Shh, I won't tell nobody. You're attracted to the chair. You're attracted to everything, gravitationally speaking. Not like love speaking. So everything in the world you're attracted to. Everything, gravitationally speaking. Write that down. You, everything, gravitationally attracted. Okay, here's why you're not flying off to things. Because the strength, write this sentence down, the strength of the force of gravity between two objects depends on two factors, those factors. So, the mass of the object, the bigger the object, the more attracted we're going to be towards it. In the distance, the closer we are, the more attracted we are towards it. So let's explain this. By the way, pause the video if you need to write that down. Okay? So, here's a little two spheres. They're gravitationally attracted towards each other because everything is attracted towards each other. Now, if the object was bigger, gravity increases. So look, the red lines indicate gravity. So the bigger spheres, the more gravity between them. So let's think about this. Why aren't you flying towards my apple? Why is my apple going towards the ground? Because the Earth is bigger than you. Newsflash. So this is going to have more gravitational attraction to the Earth because the Earth is bigger than your body. That's why my apple isn't coming towards you. Does that make sense? If I drop this on Jupiter, a bigger planet, it's going to be more attracted to Jupiter than it is the Earth because Jupiter is bigger. The apple is going to be more attracted to the sun than Jupiter because the sun is way bigger than Jupiter. The bigger the object, the more gravity. Okay. The distance also impacts it. So you're like, dude, Millis, I've never flown into the sun before and it's way bigger than Earth. Hey, here's why. You haven't flown into the sun before because you're way closer to the Earth than you are to the sun. The sun is a million Earths can fit into inside the sun, right? So the sun is like a million times bigger than the Earth. But you're on Earth. So if you are standing precariously on a ladder and you fall, you're not going to fall towards the sun, which is 93 million miles away. You're going to fall the 10 feet to the Earth. Hopefully only breaking a leg, not like your neck or anything. So the closer you are, the more gravity. The bigger you are, the more gravity. So, which gravitational force is greater? I have two choices here. You in whatever device you're using, or you in the building you're in. What is going to be a greater force? Write that down. Okay, what's going to have a greater gravitational force? The force between the Earth and the Sun, which they're attracted to each other, or the first force between the Earth and the Moon? Write down your choice. Number 3. Okay. Are you going to have more gravitational attraction between an elephant in the St. Louis Zoo or an elephant that's like roaming around in Africa? Think about this. I think there's one more. Hey, what about you and Obama? Do you have more gravitational attraction between Obama? Or do you have more gravitational attraction to Mr. Finner, who's probably in the state of Missouri right now, and Obama's probably not in the state of Missouri right now? Finally, in the same room, if there was a mouse in the room, would you have more gravitational attraction to the mouse? Or if there's a fly in the room, would you have more gravitational attraction to your fly? Let me highlight your answers here. See if I'm smart enough to do that. Ha-ha! Success. Okay, the building you were in is bigger than your device. Unless you have the iPhone 6, that's pretty big. So you in the building you're in is going to have a greater attraction because of the size of the building. Now, the Earth is the same size, but the Sun and the Moon is what's different. We're going to say the Earth and the Sun are going to have a greater gravitational attraction than the Earth and the Moon because of the size of the Sun. The elephant in Africa versus the elephant in the zoo. If they're the same exact elephant, just different locations, we're going to go with the elephant in the zoo because it's closer. Obama and Mr. Finner are about the same size. Mr. Finner's in our state, probably in the same county we're in. So we're going to say Mr. Finner has more gravitational attraction. Again, I won't let him know that you're attracted to him gravitationally speaking. Finally, if you're in the same room with a mouse, you're in the same room as a housefly, you're going to have more gravitational attraction towards the mouse because the mouse is bigger than the fly. If you have any questions, make sure you let Ms. Burkhart and I know. Make sure you write down the correct answers. Okay. Now we have another piece to this. We have mass and weight. Mass, you should have learned this in 6th grade. Mass is the amount of matter in an object. Weight is a measure of the force of gravity on the object. So I have a toy car here. The mass is not going to change no matter what. If I was to weigh this car, the weight would be how much gravity it takes to hold the car down, which it takes probably like 1/4 pound to hold this car down. It takes less weight to hold down this little toy skateboard thing. Because the toy skateboard's smaller, so it has less weight holding it down, less gravity pushing it to the earth. It takes far more gravity to push your body to earth than it does this toy. That's why you weigh 100-something pounds, most likely. Or maybe you're in a really small kid and you're like 70 pounds. Who knows what you are. Why does this matter? Because the moon itself is way less gravity, has way less mass than the Earth. It's about a sixth of the size of Earth. The moon, to do that diameter of the moon, it equals about the length of the United States. Since the moon is so much smaller, it has less gravity. Think of the pictures you've seen of the astronauts. The astronauts were able to bounce pretty high on the moon. That's because there was less gravity holding them down. Later in this unit, you're going to be doing a worksheet where you'll calculate your weight in different planets. Your weight will change because the size of the planets change. Some planets you're going to weigh a ton. You're going to feel like Fatty McFatterton. Some planets you're going to weigh an itty bitty amount, the size of like a 2 or 3-year-old. So, again, right, make sure you have this down. The mass of the moon is significantly less than Earth, so it has a sixth of the Earth's gravity. So if you weighed 125 pounds on Earth and your mass was 56 kilograms, on the moon, you're going to weigh 20 pounds. We just divide by 6. But your mass is going to be the same. This little girl did not change her size, so the amount of matter in her body is still the same no matter what location she's at. So the mass always remains consistent, while the weight changes. Okay, Newton, Isaac Newton, the guy who figured out the whole gravity shindig, also figured out what makes a planet go around the sun, or makes the moon go around the Earth. So he concluded there's 2 factors holding it together. He concluded that gravity was one, and this funky I word called inertia. Can you say inertia? Inertia. It's funny. Inertia, I'm going to talk about in a second, but gravity and inertia combine to keep the moon in orbit around the Earth. So if you look at this picture, we have the lovely Earth here, and we got the moon. Gravity is pulling the moon down. That's what it wants. The moon and the Earth are attracted, and it wants to bring them together, much like if you fall off the ladder, you fall to the Earth. The Earth is attracted to the moon, and they want to collide. However, they have never collided. Collided? Is that the right word? Collided? I don't know. They've never come together before because of inertia. So let me grab a different color. Can I do that? Yeah, I can. So inertia means it's just the motion pulling it forward. So gravity is pulling it this way, inertia is pulling it that way, and those two combine, let's find a different color, result in the path, which we call, if you remember, an orbit. So the combination of gravity and inertia, they equal out into the orbit around the Earth. So again, I want you to write the definition of inertia. Inertia is an object's motion will stay in motion, and an object at rest will stay at rest. I have a lot of things sitting on my desk right now. The toy car was one of them. The toy car is not going to start rolling off my hand. It's going to stay at rest unless I push it, which is an outside force. So it's just going to stay there. The stuff on your dresser isn't going to just fly off on its own. It's at rest. It's going to stay at rest until something forces it off. So that's why I have that little desk here. All these things are going to stay here until something pushes them off. However, this guy on the bike, okay, if he's going 60 miles an hour, like the bike says 60 miles an hour, the motorcycle, his body is also going 60 miles an hour. So if he stops his bike, all of a sudden when you apply the brakes, you're only applying brakes to your bike or your motorcycle. You don't have brakes on your body. That's why your body flies forward. My brother totally did this when he was a kid. He applied the brakes to his bike. He used the front brake. That's not a good idea. So his body flew over the handlebars because his body was in motion, and it wanted to stay in motion. And so he flew over the handlebars, lost his 2 front teeth, which he already lost them once, so that wasn't good, right? This is why your car has a seat belt. When your mom is trying to save a little squirrel's life crossing the street, she's going 80 miles an hour on Highway 40, she slams on her brake, your body was also going 80. So your body flings forward. That explains why your coffee spills and why your phone flies across the car. Because they were in motion at 80 miles an hour and they want to stay in motion. Rockets use inertia to get places. In 2008, I think, or 7, a probe left the Earth to go to Pluto. And it's coasting to Pluto a few thousand miles an hour for the last 8 years. And it doesn't need any gas, because once it's in motion, it'll stay in motion. Because there's no air friction up there, no air resistance. So it's going to stay in motion forever. So again, here's that picture again. You got gravity attracting the moon and inertia pulling it this way. So when they combine, they make the lovely orbit. You have to know that. That's exactly what the standard is asking you to know, why this orbit exists. Okay, so here's what's next. You have an online exploration, the new next. That will help you understand the gravity, inertia, and orbit stuff. And then you have inertia stations. The inertia stations to help you familiarize yourself with inertia itself. I want you to pay particular attention to the hula hoop marble activity, because the hula hoop is going to represent the gravity, and then you're going to give the marble some momentum, which is the inertia, and you're going to see it orbit. If you need help, come see us. This is a new concept, and I know you may not be familiar with it. Okay, until next time, see you later, alligator.